In this video, we have Mrs. Frog stepping in for me. So what we've got here is our big summary of our EAS reactions. Okay, so this covers all of the primary reagents. The next section that we move into is then what happens when you don't start with benzene. So when we start with benzene, all of these hydrogens are identical all the way around. So it doesn't matter which one I do a substitution for. But what happens if, say, I put on something else, atom X? Well, now those hydrogens aren't all the same, and this is where that ortho, meta, and para terminology would come into play. We have to be able to evaluate and decide how does that group affect the overall reaction. And so before we actually get into the details of how that actually affects it, what I want you to do is to see what you can manipulate with this. So we've got 4 different reactions here, and the way we would do this in class is that you would pick any one, decide on a product, and then we would kind of group it out and get people into groups to see if you all picked the same product, showed the same mechanism, and looked at all that fun stuff. So instead, what's going to happen here is I'm going to do the first one. I will do one for you with both results. Okay? And then we can talk about those a little bit. You should then be able to go through 2, 3, and 4, similar process that I go through for 1, and you should probably do it for all 3, okay? Because that's going to help solidify how and why these things are working the way they do. If you can get that understanding down before you start the next video, that's going to be ideal. Okay? There's a little challenge kind of question if you wanted to throw that in at the end. One of these reactions is not expected to produce products. Okay? So you should be able to explain that. Before we get into that, realize that to start the assignment, we are going to assume that all of these reactions will occur once, and they'll follow our standard EAS chemistry. Okay, so let's go ahead and take a look at reaction 1. So we'll clear up some of the screen so that we can see what's happening here. And realize there's 3 potential products. Oh goodness, so I'm going to draw 3 potential mechanisms. We'll call our ortho, our meta, and our para. Yeah. So if we were to set this up, okay, we'll start with the ortho. We're going to take the electrons in that pi bond, and we're going to share them with our electrophile. This would undergo our standard nucleophilic addition elimination, or actually not our nucleophilic addition elimination. Sorry, I just realized, forgot that before we even do that, these reagents react with each other. We end up forming the aluminum tetrachloride, and then we would also get, remember, the acylium ion. From here, now the pi bond from our benzene can come in and react. Right? That shuttles the electrons up. The result of this is that we get our benzene structure. There's our methyl. And remember, we said we want to react at the ortho position. So that means I'm going to place it at the ortho position. That was way too crowded at that side, of course. Okay, so we'll CH3, C, carbonyl. There's our benzene ring. There's the other CH3. The other double bonds we did nothing with, and then we would have a carbocation here. And that carbocation is not particularly stable. It could be stabilized via resonance. It's drawn a bit sloppily, so let's try that again. We've got, again, our CH3, C, carbonyl, double bond, positive charge, double bond, CH3, and again, another resonance. and I keep forgetting the space for that acetyl group, CH3C. There's our positive charge. I'm showing it in the ring here. The in versus out of the ring doesn't matter. Sometimes I'll get questions about that. It's completely irrelevant. And then we have to remember that that carbon that reacted still has an implied hydrogen. Remember, these are our sigma intermediates, so we still have that implied hydrogen. So what we can do is take the electrons. Oh man, my computer is now having issues connecting, so we'll just talk through it while I continually hit reconnect. Our electrons in that carbon-hydrogen bond, we would go ahead and steal those and place them into the bond. The end result would be our final answer, where we now have done the full substitution. Here's our CH3, double, double, double. Okay? So that would be our potential product from the ortho stance. We also talked about it potentially reacting from the meta stance. Okay, so here's our meta position. This is going to be a very similar mechanism. We can use the exact same pi bond, okay, except now when we draw out our result, of course this is going to get a bit crowded. Whoops. When we draw out our result, we'll just show that acetyl group connected at the meta position instead of at the ortho. Okay? Our positive charge would now be up there. We didn't react the other double bonds. We could again go through resonance, electrons shuttle. And for those of you wondering, oh my gosh, this is an awful lot of resonance. Do I need to go through and do this? Yes and no. Okay? Ultimately, what you could do is memorize the conclusion that the resonance gives you, and with that conclusion, thereby know all your answers. Okay? But that's largely going to depend on your ability to memorize and making sure to memorize correctly, because it will change and shift on you based off of the resonance. Carbonyl, CH3. Okay. Again, we have that implied hydrogen. We could take those electrons, form our final structure, where we now have the carbonyl at the meta position. Okay. Officially, we still have the para. Oh, I'm going to have to turn the structure because I don't have a whole lot of space here to be able to draw it. So I'm going to rotate it so that we can fit this in here. Here's our CH3. Due to resonance, it's not really going to matter where I place that positive on whichever side. Okay. So again, our resonance shuttles into this, and we end up drawing more resonance structures. Okay. So as I continue to draw this out, hopefully what you can do is spend some time actually looking at the structures and decide, is there a difference between these? And for those of you going, well, yeah, it's ortho, meta, and para. Yes, okay, but take it a step further. Do your products, should there be a preference for one product over the other? Okay, that preference always comes back to energetics, and those energetics are seen in your mechanism. Okay, that's the point of drawing mechanisms, is so that we can try and evaluate those charges. Again, there's that hydrogen. We would have our final answer where it is at the para position. Okay. The products themselves aren't going to be particularly different in energy, though we could try and make some arguments there. We could make the argument the ortho is going to be high in energy, or higher in energy than the other two products. And that would be because the ortho, which I said was the red one, the ortho has these two groups sterically close to each other. So there's some steric kind of repulsion, okay, electron bumping, a little bit less fancier way of saying that, okay, and that could be an argument against the ortho. But then what about the meta and the para? Okay, well, so to really evaluate our difference, we need to drill down to each of our resonance structures. Okay, and so they're aligned roughly next to each other. So if we start with the red one, so we'll go with our ortho, it is a secondary with resonance. The meta was a secondary with resonance, and the para was a secondary with resonance. So this is where some people would say, well, there's no difference, so all three products are accepted. But you have to evaluate all of your resonance. You can't just cherry pick which ones you want to look at. So if we continue on, secondary with resonance, secondary with resonance, para says tertiary with resonance. Well, the tertiary carbocation is more stable than the primary carbocation or even the secondary carbocation. So I would expect that intermediate to be super stable. If the intermediate is stable, I then increase the odds of doing that first step, which then means the second step could happen. So based off of that, we're now kind of expecting the para to be a good product. Okay, stable intermediate, it's going to favor. Okay, but again, we can't cherry pick. We need to continue to move on. We move to the ortho, and we see up here, it's also a tertiary. We look at the meta. The meta comes in as a secondary, and the para comes in as a secondary. So if we summarize this result, the ortho has a kind of bad steric repulsion. It also has good intermediate. The para has a good intermediate, and then the meta has nothing. Nothing favors the meta. So what does that suggest? Well, that would suggest that if the group that I'm starting with just a CH3 up there, if I see that again, I would predict that the para substitution would be the most likely to occur because it generates the most stable intermediate and it doesn't have the steric repulsion of the ortho position. Right? That's a lot of work to go through and address, but that's what you should do. Okay? And what you should do that, and if you're going to take notes, now's the time to hit pause because we're about to delete it all. You should do that with 2, 3, and 4. So you should have a total of, 9. So 2, 3, and 4, each of them should have the ortho, meta, and para drawn out for your substitution, and you should see what those results are and decide which one's more or less stable. Okay? There's 4 things here, 4 reactions, and that was done kind of intentionally because there's really only 3 substitutions. So once you do all of your substitutions, see if you can then find more patterns. So for instance, 1, we said para was favored. Okay. Well, is para favored for any of the others? Okay. Let's say para was favored for this one. So what? Let's not do that one because I can't find an easy pattern. Para was also favored for 4. And this is hypothetical. I'm not saying 4 is para favored. Okay, so let's say 4 was para favored. Now what we should go through and do is compare 1 and 4 and trying to decide what do they have in common that would explain why they both favored para. So in this particular case, one might go through and say, well, we just swapped the order of the reagents. Well, changing the order of the reagents makes a huge deal. Okay? That can go from a reaction working to not working. So just saying you swapped the order of the reagents doesn't count as why you'd be favoring para. Okay? Remember, it came down to the stability of the intermediate, and the clutch was drawing a tertiary carbocation. So we're looking at that atom being carbon. And if we looked at the other one, oh my goodness, that is also a carbon. So we could go through and now start to compile evidence and say, if there's a carbon connected to the ring, it goes to the para position. That's the idea of drawing these conclusions. You look at the evidence and you start to make those comparisons. One of the things that happens in OChem is that everything you've studied, someone has done this already. The idea that you should be moving through is trying to find out what that something was so that you understand the conclusions that come out of it. Because when things go sideways, you now know why they went sideways. In this particular case, this conclusion of para and para was entirely false. Okay? But you should go through, draw all three intermediates, and once you think you've started to notice a pattern, or maybe you haven't noticed a pattern, but you've at least done it, then you can move on to the next video that'll start to address what that pattern was and why it was so visible and what conclusions can ultimately be drawn from it. So with that, Mrs. Frog would like to say thank you for listening and good luck.